Installed on Monday as Rouse Ball Professor at Cambridge, known for his elegant lectures, Timothy Gowers needs no introduction. An immense intellect, analyst and commentatorist, he receives the Field Medals in 1998 in Berlin. He's currently a CMI Prize Fellow. Timothy Gowers will speak today on l'importance des mathématiques.
It is with some disbelief that I stand here and prepare to address this gathering on the subject of the importance of mathematics. For a start, it is an extraordinary honor to be invited to give the keynote address at a Millennium meeting in Paris. Secondly, giving a lecture on the significance of mathematics demands wisdom, judgment, and maturity, and there are many mathematicians far better endowed than I am with these qualities, including several in this audience. I hope, therefore, that you will understand that my thoughts are not fully formed. If I'd been asked to speak on this subject 5 years ago, I would have given a completely different lecture, and I'm confident that in 5 years' time it would again have changed. My title, which I did not actually choose myself, though I willingly agreed to it, also places on me a great burden of responsibility. After all, I am speaking to an audience which contains not just mathematicians, but journalists and other influential non-mathematicians. If I fail to convince you that mathematics is important and worthwhile, I will be letting down the mathematical community and also letting down Mr. Clay, whose generosity has made this event possible and is benefiting mathematics in many other ways as well. Unfortunately, if one surveys in a superficial way the vast activity of mathematicians around the world, it is easy to come away with the impression that mathematics is not actually all that important. The percentage of the world's population, or even of the world's university-educated population, who could accurately state a single mathematical theorem proved in the last 50 years, is small, and smaller still if Fermat's last theorem is excluded. If you ask a mathematician to explain what he or she works on, you will usually be met with a sheepish grin and told that it is not possible to do so in a short time. If you ask whether this mysteriously complicated work has practical applications, and we all get asked this from time to time, then there are various typical responses, not always all that impressive. One is the line taken by the famous Cambridge mathematician G.H. Hardy, who was perfectly content, indeed almost proud, that his chosen field, number theory, had no applications, either then or in the foreseeable future. For him, the main criterion of mathematical worth was beauty. At the other end of the spectrum, there are mathematicians who work in areas such as theoretical computer science, financial mathematics, or statistics, areas of acknowledged practical importance. Mathematicians in these areas can point to ideas that have had a big impact, such as the Black-Scholes equation for derivative pricing, which has transformed the operation of the financial markets, and the public key crypto system invented by Rivest, Shamir, and Edelman, which is now the basis for security on the internet, and which, as has been pointed out many times, is an application of number theory that Hardy certainly did not expect. Also, at the applied end of the spectrum, there are many mathematicians whose work has intimate connections with theoretical physics. Actually, it's not obvious that something like unifying general relativity and quantum mechanics would have direct practical applications, since today's physics already provides us with predictions that are accurate to within the limits we can measure. But one never knows. And in any case, such a breakthrough would be of absolutely fundamental interest to science, and indeed to anybody with the slightest intellectual curiosity. If mathematicians can make a contribution here, then they would at least be able to point to a huge external application of mathematics. Most mathematicians, including me, lie somewhere in the middle of the spectrum when it comes to our attitude to applications. We would be delighted if we proved a theorem that was found to be useful outside mathematics, but we do not actively seek to do so. Given the choice between an interesting but purely mathematical problem and an uninteresting problem of potential benefit to engineers, computer scientists, or physicists, we will opt for the former, but we would certainly feel awkward if nobody worked on practical problems. Actually, this attitude is held even by many of those who work in more practical seeming areas. If you press such a person asking for a specific example of an application in business, industry, or science of their own work, as opposed to an application of a result in their general area, you will often, though not invariably, witness an uncomfortable reaction. It turns out that a great deal of the research in even the so-called practical areas is in fact not practical at all. I'm not trying to draw attention to some sort of scandal by saying this, as I hope to demonstrate this phenomenon is a natural and desirable consequence of what it means to view the world mathematically. The reason for it is that mathematics is a two-stage process. Rather than studying the world directly, mathematicians create so-called models of the world and study them. This applies even to the simplest mathematics. After the age of 4 or 5, we do not study addition by actually combining groups of objects and counting them. Instead, we use an abstract mathematical construction, or model, known as the positive integers, that is, the numbers 1, 2, 3, 4, 5, and so on. Similarly, we do not do basic geometry by cutting shapes out of paper, partly because it is not necessary, and partly because in any case the resulting shapes would not be exact squares, triangles, or whatever they were supposed to be. Once again, we study a model, a sort of idealized world that contains things that we do not come across in everyday life, such as infinitely thin lines that stretch away to infinity, or absolutely perfect circles. Moreover, it does not contain untidy worldly things like chairs, or human beings, or hamburgers. If one works in a practical area of mathematics, then there will be two conflicting criteria for what makes a good model. On the one hand, the model should be accurate enough to be useful, and on the other, it should be simple and elegant enough to generate realistic and interesting mathematical problems. It is tempting, as a mathematician, to attach far more importance to the second criterion, mathematical interest and elegance, than to the first, accuracy, even if this means not immediately contributing to the gross national product of one's country. I'd like to give a quick example of this, which does come from theoretical computer science. So I shall just discuss quite a well-known problem. What I've got here is a network, or what mathematicians would call a graph. So the network contains various, you can call them nodes or vertices, whatever you like. And the problem associated with this network, or at least the problem I'd initially like to discuss, is it possible to colour in these circles here with two colours, let's say red and blue, in such a way that you never have the same colour joined by one of these lines? Well, how would we go about doing that? We could just start trying to do it. Perhaps we could colour in this node here with red. Once we've coloured this one red, if we've only got red and blue, then this one has to be blue, and this one has to be blue. Once those two are blue, this one has to be red, this one has to be red, this one has to be red. And you can see that actually once you've put in the first colour, everything else is forced. So let me just show you what the result of this analysis is. I can get it to fit. So here was the red. It might as well be red. If it was blue, it wouldn't make much difference. It would just swap red and blue around. And so A was the first one we coloured in. Then we were forced to do these two Bs in blue. Then we were forced to do the Cs in red again. And then we were forced to do these three Ds in blue. But once we've done that, we notice that we've got a blue next to a blue. And everything's gone wrong. But because we were forced to do everything that we did, then we were forced to go wrong. In other words, it is impossible to colour in these circles with just two colours in such a way that you never have two of the same colour linked to each other. Now that's quite a simple argument, as mathematical arguments go, and what that translates into is that if you want to devise a computer program to solve this problem for you, when you say instead of having the 12 nodes that I've got here, say you had 1,000 nodes and it'd be rather tedious to go through all this process, you can do it. And, well, I've written it for 100. If n stands for the number of nodes, then roughly n squared will be the number of steps that this procedure takes. I'm slightly taking into account that a computer can't just sort of look and see that there's an edge in quite the way that we can. So that's why I've put n squared there. Now let me consider a superficially rather similar problem. In fact, superficially very similar problem. because I'm going to put up another of these networks. It's a little bit more complicated, perhaps. Well, can we colour this one with two colours? No, we definitely can't, because there's a triangle here, and you certainly can't, if you've got this one red, and that has to be blue, and that has to be blue, and you've had it. So it's immediately obvious that you can't colour that one with two colours, but perhaps you could do it with three. Well, how are we going to go about solving that? The question, can you do it with three colours in such a way that you never have the same colour linked to itself? Well, we could start over here and put that one red, but then what do we do? That one could be blue, or it could be green. What should we do? Well, so far, perhaps we could just say without loss of generality, it's blue. And then here, well, that one could be green, or it could be red. And you can't say without loss of generality anymore, because this one's already red, so it sort of makes a difference, whether it's red or blue, or at least it may make a difference. Now, if you try and do it by this sort of method, what you find is that you may well be able to fill in a few of them, and then somehow you get into trouble over here. You find that you can't put the colours in. To get out of that trouble, it may well be that you can't just take one step back. You have to take sort of several steps back and maybe change something that you did right near the beginning. And it turns out that actually, well, I would like to say with great certainty that there is no way of doing it, or no sort of quick way of doing it. That's actually an unsolved problem, but there is no known quick way of doing it. What would be a slow way of doing it? A slow way of doing it would be just to try all possible colourings of three things. So every conceivable assignment of red, blue and green to these nodes, and just see if you find one that happens to work. Well, I didn't do that, actually. Of course, I chose the colours first and then drew the network. But it can be done in this particular case. There is a colouring with red, blue and green, and you never have, unless I've made an embarrassing mistake, you never have the same colour linked to itself. Now, supposing you had 100 vertices and you did it by the crude method that I described, of just checking all possibilities, well, it would take of order 3 to the 100, and then each time you wanted to check it, you've got 100 squared. Actually, I didn't put enough zeros on the end. It's an even bigger number than I've done. There should be 2 more zeros. So that is, as I've written it, 3 to the 100 times 100. It should be 3 to the 100 times 10,000. Now, you don't have to be a great expert in computer science to know that if you've got that number of steps, then the calculation is going to take too long. In fact, it would take too long even if you had the whole age of the universe to play with and every single atom of the universe at your service. It just can't be done. Now, what do computer scientists say about this? They want to distinguish between step-by-step procedures that are practical and step-by-step procedures that are not practical. And the convention is the following. If n is the size of the problem, which in this case might be the number of nodes, then a procedure is practical if it is no worse than a polynomial in n. So a polynomial is some expression like this, 100n to the 8 plus 73 n to the 6, some expression that looks a bit like that. Then the algorithm or the procedure counts as efficient, and if you can't say that there's some polynomial that gives you an upper estimate on how long it takes, then you say that it's inefficient. Now, why is that a good convention? Well, there are sound mathematical reasons for it, which I don't want to go into. What I want to point out here is that from a strictly practical point of view, it is not a good convention, because if you, e.g., had 100 vertices and you took this particular polynomial, that is the number of steps you would need, and that is, although not as big as the number I had over there, is still a very, very big, rather impractically large number. So computer scientists, or at least some computer scientists, deal with algorithms that you might call practical in theory, but not practical in practice. Now, there are, as I say, very, very good reasons for that, and which I don't want to go into, but just to say that you can be working in a practical seeming area in a rather theoretical way. I don't want to pretend that computer scientists actually think their algorithms are practical. Of course they know the distinction that I've just drawn attention to. So to summarize what I've said so far, most mathematicians, including those who work in useful sounding branches of mathematics, do not work on problems with direct practical applications. It would be dishonest of me to argue for the importance of mathematics by trying to pretend that this was not so. Instead, my task will be to explain why, despite this fact, mathematics is a worthwhile endeavour and why it should be supported. And I will give 2 arguments. The first, based on the practical utility of mathematics, despite what I have just said, and the second on its cultural value. Well, it may look as though I've been trying to convince you that mathematics is a useless subject, but in fact, all I have claimed is that a typical mathematician does not actively try to be useful. And these are 2 very different statements. They're different because there is an important distinction between the collective result of an activity, and the individual motives of the participants. Let me give an example of this from outside mathematics. Some capitalist economies are based on the premise that individual greed and selfishness, if I can use somewhat emotive terms, can act for the collective good of society. The greed causes people to strive to become wealthy, and this benefits the entire economy in many ways, such as increasing the tax revenue for the government, which can then be spent on hospitals, schools, public transport, and so on, or causing companies to be set up, which provide livelihoods for many people. The individuals need have absolutely no interest in whether other members of society have satisfactory lives, provided that sufficient social order is maintained, but in an indirect way, their activity does benefit others. Of course, not everybody agrees that economies such as I have briefly described are a good thing, and the last thing I wish to do is to let politics intrude on a mathematical lecture. However, it is surely not controversial to state that individual selfishness, so to speak, can lead to public good, and I wish to argue that something similar happens in mathematics. Although individual mathematicians are motivated primarily by a subtle mixture of ambition and intellectual curiosity, and not so much by a wish to benefit society, nevertheless, mathematics as a whole does benefit society. I would now like to examine in more detail why this is. One straightforward answer is this: mathematics is cheap, and occasionally produces breakthroughs of enormous economic benefit, either directly, as in the case of public key cryptography, or indirectly, as a result of providing the necessary theoretical underpinning for science. If you were to work out what mathematical research has cost the world in the last 100 years, and then work out what the world has gained in crude economic terms, then you would discover that the world has received an extraordinary return on a very small investment. And I haven't even mentioned the fact that those who engage in mathematical research also teach very bright students, many of whom do not themselves become mathematicians, but rather use their mathematical training in ways that directly contribute to the world economy. Taken as a whole, then, mathematics is undeniably important. However, a cost-cutting finance minister will notice a gap in the above argument. Might it not be possible to achieve the same benefits more cheaply? If the benefits of mathematics come from teaching and a few breakthroughs, while most mathematicians get on with their interesting but useless research, then why not cut the research funding to the useless areas and just support the teaching and the more practically oriented mathematics? One of my main objectives today is to expose the fallacy, or rather fallacies, that would lie behind such a proposal. The first one is the idea that it is possible to identify the areas of mathematics that will turn out to be useful. In fact, it is notoriously hard to predict this, and the history of mathematics is littered with examples of areas of research that were initially pursued for their own sake and later turned out to have completely unexpected importance. So I could mention the RSA algorithm yet again. A more fundamental example is the non-Euclidean geometry of Gauss, Bolyai, and Lobachevsky, which is internally consistent, despite such apparently paradoxical phenomena as the existence of triangles with angles not adding to 180 degrees. This paved the way for Riemannian geometry, which seemed to be an example of pure mathematics par excellence, until it turned out to be exactly what Einstein needed for his general theory of relativity. A recent and celebrated example is provided by the theory of knots, and let me briefly say a little bit about that. It will be brief. So this is directed chiefly at such non-mathematicians as there are in the audience, because it's quite a familiar example for mathematicians. So what I've drawn here is a picture of what a mathematician means by a knot. Mathematicians don't mean a long piece of string with a little sort of tangle in the middle. They mean exactly that, except that you take the two ends and fuse them together into the sort of loop. So let's have a look. I've just drawn a picture of a few knots. Down at the bottom, if you've got reasonable powers of visualization, you'll see that there's a knot that in a certain sense is less interesting than the other ones, because you can just untwist it and it just turns into a loop. And for that reason it's sometimes known as the trivial knot or the unknot. Over here we've got some more sort of interesting, quite nice looking ones. And the sort of problem that knot theory is concerned with is how to classify the various knots. Now I've just said that this bottom one is basically the same as a loop. Now this idea of basically the same is you take your tangled loop and you're allowed to deform it, move bits of it around without breaking it at any stage. And so then if you do that, then it's still really the same knot. Now, you could ask, is this knot the same as this one, for example? Could it be that if I cleverly manipulated this knot, I could turn it into this one? If anybody can give me a quick answer to that who's not an expert in the subject, I'll be extremely impressed, because actually it's a rather hard problem to do it. And maybe just to illustrate that, I'll tell you that this knot here is the same as this one here, and the others are all different. So it's not obvious just looking at them. Now, you could discover that this knot was the same as this one simply by messing around with this knot and moving it about and just trying to produce this one. And if you managed, you could say, lo and behold, the knots are the same. But the opposite problem, trying to show that, say, that one is not the same as that one, is much, much harder. You could try for 10 years to do it and fail, but that's no evidence that some cleverer person couldn't come along and do it instead. Now, that's all I want to say about that. The theory of knots is absolutely fascinating, but the main point I want to make about it is that it looks rather like an amusing game. Let's just think about these knots and see which ones we can distinguish from one another. But as it happens, it turns out to have very deep and fundamental links with theoretical physics. This was discovered after some work of Vaughan Jones and Edward Witten, and came as a great surprise to mathematicians. So you have to be careful in thinking that a piece of mathematics is just pure mathematics. So mathematicians can tell their governments, if you cut funding to pure mathematical research, you run the risk of losing out on unexpected benefits, which historically have been by far the most important. However, the miserly finance minister need not be convinced quite yet. It may be very hard to identify positively the areas of mathematics likely to lead to practical benefits, but that does not rule out the possibility of identifying negatively the areas that will quite clearly be useless, or at least useless for the next 200 years. In fact, the finance minister does not even need to be certain that they will be useless. If, say, a large area of mathematics has only a 1 in 10,000 chance of producing economic benefit in the next 50 years, then perhaps that at least could be cut. You will not be surprised to hear me say that this policy would still be completely misguided. A major reason, one that has been commented on many times, and is in a way implied by the subtitle of this conference, a celebration of the universality of mathematical thought, is that mathematics is very interconnected, far more so than it appears on the surface. The picture in the back of the finance minister's mind might be something like this. There are just a few areas of mathematics. Some of them are useful, some of them may be useful, and some of them are pretty obviously not useful. And they're all sort of reasonably well distinguished. So, you know, the finance minister would say, well, let's cut that one and that one there, and maybe we can give some money to that one just to encourage it. And the useful ones we like. You know, that would be the kind of mental picture. Of course, there are many more areas of mathematics than that slide suggests, but maybe the finance minister wouldn't know that either. Now, here's what I would think was a slightly more accurate picture. Still actually an enormous oversimplification, but more accurate. Something more like that. Well, you'll see that you can sort of see that some areas are a little bit denser than others. And maybe you could just about decide that you're going to call that an area of mathematics, but the boundaries are not terribly well defined. Just for the fun of it, let me just superimpose the initial naive picture of mathematics onto this one. So there we are. So this useless area over here, if you try to cut it, you're also cutting a lot of links to an area that's useful. And so you run quite a serious risk by so doing. So in particular, if mathematicians work on difficult practical problems, they do not do so in isolation from the rest of mathematics. Rather, they bring to the problem several tools, mathematical tricks, rules of thumb, theorems known to be useful in the mathematical sense, and so on. They do not know in advance which of these tools they will use, but they hope that after they have thought hard about a problem, they will realize what is needed to solve it. If they're lucky, they can simply apply their existing expertise straightforwardly. More often, they will have to adapt it to some extent. Perhaps it will be helpful if I show another two pictures, this time explaining in a very vague way what it is like to solve a mathematical problem. So again, I'll start with a naive picture of what it's like to solve a mathematical problem, and then I'll give one that's a bit more realistic, but still an oversimplification. So that might be the naive view. You start with a certain amount of knowledge, You think for a while, you have a brain wave, you haven't solved it, so you think a bit longer, you have another brain wave, still haven't solved it, so you have another brain wave. You're doing quite well if you have 3 brain waves, actually. And then you think for another while, and you've solved it. And that's the whole picture. Well, any mathematician will recognize that that is not quite what it feels like. So again, I stress that the next picture is also a huge oversimplification, but it's just less of an oversimplification than the one I've had before. So it'd be more like this. You start with some existing knowledge, which I've written in blue down at the bottom. And we're not quite sure what's going to be useful. It turns out that this one bit here and that bit there were useful. These green nodes here denote sort of dead ends, ideas that were had. Somebody attempted to solve it by following this sort of green path here, but it didn't work. And in the end, eventually they found this sort of red thing that led to the final proof of the theorem. And so it's important that you've got a whole lot of parts here that you don't use, as well as a whole lot of parts that you do use. That's the real point that I want to stress. So a good way to think about mathematics as a whole is that it is a huge body of knowledge, a bit like an encyclopedia, but with the important difference that it has an enormous number of cross-references. This knowledge is stored in books, papers, and the brains of thousands of mathematicians around the world. It is not as convenient to look up a piece of mathematics as it is to look up a word in an encyclopedia, especially as it is not always easy to specify exactly what it is that one wants to look up. Nevertheless, this so-called encyclopedia of mathematics is an incredible resource. And just as if one were to try to get rid of all the entries in an encyclopedia or all the books in a library that nobody ever looked up, the result would be a greatly impoverished encyclopedia or library. So any attempt to purge mathematics of its less useful parts would almost certainly be very damaging to the more useful parts as well. So far, I have simply stated that mathematics is full of surprising connections. Any mathematician will happily confirm that statement and be able to give examples from his or her experience. Indeed, discovering surprising connections is one of the great joys of the subject. I would like to illustrate the interconnectedness of mathematics with an example in which I played a small part. I just want to describe 3 or 4 problems. I shall describe them rather briefly. So that is because my main purpose is not so much to go into great mathematical detail about the problems, it's just to convey somehow the flavor of the problems, and then I'll say why I want to convey the flavor of them. So let's look at these sequences of numbers, 5, 11, 17, 23, 29, and then there's some other ones. If you look at it, you'll notice that the jump from 5 to 11 is 6, then it jumps up by another 6 to 17, by another 6 to 23, and so on. So this sort of sequence where you jump by a regular amount is called an arithmetic progression. Here's another one, 7, 19, 31, 43. The jump is 12. And here the jump is 30, 11, 41, 71, 101, 131. And similarly for the bottom one. Now you might ask why I didn't continue those sequences further. Well, the reason was that all these numbers in black here have in common that they are prime numbers, something of great interest to mathematicians. And had I tried to continue from 29, say I'd have gone to 35, and that's not a prime number because it's 5 times 7. And over here also are the explanations for why the next number is not a prime number. Now, once I show you that, there are some very obvious questions you could ask. The most obvious one is the second one, actually. Is there any limit to the possible size of an arithmetic progression consisting solely of prime numbers? Nobody knows the answer. I think the record that anyone's found is about 22 or 23, but that's just discovered by a computer search. It doesn't really get you any closer to a solution of the problem. Another question is, are there infinitely many arithmetic progressions consisting of 4 prime numbers? So I'll just leave that problem there. I could spend an hour talking about it happily, or more, but problem number 2. Consider those numbers at the top. 3, 5, 8, 13, 14, and so on. What have I drawn these lines for? Well, notice that 5 minus 3 is 2, and that's the same as 29 minus 27. So I've picked out quadruples of these numbers, so it's like 3, 5, 27, 29, where the difference of 2 of them is the same as the difference of another 2. So another example, 14 take away 8, that's the green example, is the same as 35 take away 29. They're both 6. So I'll just leave that there. Now here's something else. If I take a set of numbers 1, 2, 4, 6, 23, 29 and call that A, what I mean by A plus A is the set of all numbers that I can make out of A by adding two things in A. So for example, 4 plus 6 is 10, and that's why I've written 10 over here. 23 plus 29 is 52, that's why 52 appears here. I've written down all the things I can make by adding two of those. Quite an interesting problem in certain contexts is how large the set is of numbers that you can make from your first set by adding two of them. And there's a theorem called the Balog-Semeredi theorem, which says if you have a set that's got rather a lot of these quadruples of numbers where the difference of 2 is the same as the difference of another 2, then it's not necessarily true that, so call that set A, it's not necessarily true that A plus A is small, but what you can do is pass to a rather large so-called subset. So here the subset is B, 1, 2, 4, 6. It's a subset because I've got 1, 2, 4, 6 up here, but I haven't taken the whole lot. And when I pass down to B and look at B plus B, it's quite a lot smaller than A plus A was. In fact, the ratio of the size of B plus B to B is 9 to 4, which is just over 2, whereas the ratio of the size of A plus A to A was 20 to 6. Now, roughly speaking, the Balog-Semeredi theorem says if your set has this sort of structure, it's got a lot of these, what I sometimes call additive quadruples, then you can find a large subset where when you add it to itself, you don't get something too much bigger. Again, I don't want to say anything about the significance of that just at the moment. Here comes problem 3. This is a problem known as the Kakea problem. What you do is you start with a triangle, which is here, and you divide it up into, well, in the picture, 8 sub-triangles. That's a rather mathematical word, I apologize for that. But anyway, 8 tall, thin triangles that go up to make the big triangle. And mathematicians would say, well, 8 equals n or something, so it doesn't matter that it's 8. And what you're trying to do is to take these smaller triangles and slide them around in such a way that they overlap with each other, and you want to make them overlap with each other in such a way that the triangles take up as little space as possible. Space is expensive, but you're allowed to overlap. And the pictures show a way you can do it, which is you take them in pairs, and then you slide the pairs together. That's in the first step. And then you take pairs of these pairs and slide those together. That gets you to here. And then you take pairs of these now quadruples, slide those together, and you get a funny sort of plant-like shape that has smaller area than the original triangle because you've got all this overlap. Now, it turns out that if you're clever enough, you can make the area as small as you like of the overlap. If you have 2 to the n pieces, which to the layperson is a very, very large number, if n is at all large, then you can make the area go down to 1 over n. For example, if you wanted the area to be, say, 10% of the original area, you'd need around about 1,000 pieces. If you wanted it to be 1% of the original area, you'd need around about 1,000,000 pieces. So you have to go, it has to be pretty big. Did I mean, no, sorry, 5% would be 1,000,000, I beg your pardon. Now that's not actually the real problem that I want to discuss, but it is a useful background to it because the real problem is the natural three-dimensional generalization of that problem. So what would be the three-dimensional generalization? Instead of taking a triangle, you take a pyramid, and instead of dividing it into little triangles, you divide it into tall, thin, little pyramids. Here I've got it divided into 9 little pyramids, and then you're allowed to slide those around. Now they overlap in space, so to speak, and you want to make the volume rather than the area as small as possible. Well, I decided that it was not a good idea to draw 9 overlapping cones. I restricted myself to 4, but in reality one wants to do 9. And again, for mathematicians here, actually, you want to go beyond 3 dimensions and go up to n. The big open question here is, whereas in 2 dimensions you needed a huge number of pieces to get the area to go down, maybe that's not so true in 3 or more dimensions. It's actually suspected that you do need a lot of pieces, but nobody knows how to prove it. I'll just show you a very quick picture, just because I've got it. There, that might be where you divide the base of the pyramid into many more pieces, make cones out of them, and try to slide them about to get the area as small as possible. But I think this picture is a better one to leave. And then problem number 4. I'm not going to say much about this because it's very, very much not my area of expertise, but partial differential equations, as mathematicians will know, are absolutely fundamental to physics. If you want to model anything, more or less, you come up with a partial differential equation, and what you'd like to know about it is things like, does it have solutions? If so, are those solutions smooth? How do they behave? Do they blow up after a certain amount of time? And so on. And they describe phenomena such as wave functions, the flow of heat, waves, the motion of fluids, you name it. It's got a partial differential equation to describe it. And then there are linear ones. Those are sort of relatively simple, although there are plenty that's not known about them. And then there are nonlinear ones, which are, in some contexts, more realistic, but much, much harder to analyze. So I haven't asked a specific question here. There are lots and lots of questions. Now, you may ask, why did I choose those 4 rather different-looking problems? You may have guessed the answer if you don't know it, which is that they're not as different as they look. In fact, there are very close links between them. So you can get from arithmetic progressions in primes to partial differential equations by a sequence of links. Now, if you really want to know about this, what you have to do is come here tomorrow and listen to Terence Tao, who will be talking about it in some detail. But let me just describe what 1 or 2 of these links are like. If you're looking at arithmetic progressions of primes, it's very natural, and Erdős and Turan did this, to generalize the question to arithmetic progressions in more general sorts of sets. That led to a very famous theorem of Semeradi, who solves the conjecture of Erdős and Turan. As an aside, that led to important advances in ergodic theory, which is a totally different branch of maths and surprised everybody. I was thinking about a different approach to Semeradi's theorem and came up with a lemma, which was a sort of an improvement of the Balog-Semeradi theorem, which I talked about a little earlier. Jean Bourgain noticed that he could use that lemma to improve the best-known answer so far for the Kakeya problem, the one about sliding cones about. Actually, I have to admit that Nets Katz and Terence Tao found a way of getting an even better improvement, not using the lemma that I talked about. But that's the way mathematics progresses, I think, and I don't think that completely invalidates the link. Bourgain had earlier proved that the Kakeya problem had intimate connections with the distribution of the zeros of the Riemann zeta function, intimately itself connected with the distribution of prime numbers, as Riemann showed us, which gets you full circle back to arithmetic progressions in primes, because you need to know about the distribution of primes, or you may need to, actually. And the Kakeya problem is also very closely connected to conjectures in harmonic analysis, which themselves you need for the analysis of certain partial differential equations, and that's what Terence Tao will be talking about, which is, of course, important for physics. Now, I'm not going to claim that thinking about arithmetic progressions of primes directly helps physics or something like that, but nevertheless, there's this huge interconnected web of knowledge, and you just can't afford to break bits off it. That would be my main message. So as a final cautionary tale for the hypothetical finance minister, let me also demonstrate that problems that look like nothing but fun and games can also turn out to be of direct practical importance, after all. I mean, knot theory sort of provides an example of that, but here's an even more obvious example, I would say. Timetabling. So this is something that people come across from time to time. I can't call it an impractical thing to think about. Let's imagine that let's say, it doesn't have to be this, but let's imagine that we're trying to organize some exams. And so we've got 7 candidates, numbered 1 to 7, 8 papers, so A to H. So each candidate takes either 2 or 3 papers. Candidate 1 wants to take paper A, C, and H. Candidate 2 takes B and D, and so on and so forth. The question is, we've got a rather expensive examination hall to book. We want to hire a rather expensive hall. We don't want to use it for more papers or more sittings than necessary. So how many sittings do we need? Well, candidate 1 is taking 3 papers, so there must be at least 3 sittings, but there's nothing to say that you couldn't have 2 different papers going on in the hall at the same time. So how are we going to solve this? Well, let's just think about which papers could coincide with each other and which ones couldn't. For example, we know we better not have paper A at the same time as paper C, because then poor old candidate number 1 would be trying to do 2 papers at once, and that we don't insist on. Similarly, B can't go with D, A can't go with G, A can't go with C, D can't go with E, and so on. Well, it's a bit annoying looking at this table here, so I just want to sort of represent that knowledge in a slightly more convenient form. I'll just draw a little thing here. So what I've done here is, this is paper A, and I've drawn a link from A to C to say that A and C are incompatible because candidate number 1 is taking them both. So when two papers cannot go together, I've joined them with a link. When they can go together, I haven't joined them. Now, what are we trying to do? We're trying to associate, well, let's say we're trying to do it in 3 sittings. So to each paper, we'll say, well, it'll either be the first sitting, second sitting, or third sitting. So to each of these nodes here, we'll associate the number 1, 2, or 3. What must we not do? We must not have 2 incompatible papers in the same sitting. So for example, we mustn't have 1 with A and 1 with C. Well, it's a little bit inconvenient having 1s, 2s, and 3s. Might be nice if we just put a bit of color into it and said 1 is, say, what was it, red, 2 was green, 3 was blue, or something like that. So now what are we trying to do? We're trying to color these circles in with 3 colors in such a way that you never have the same color at either end of one of these links. That problem, I hope, will remind you of something. So it can be done. So any non-mathematicians were sitting there thinking, why on earth do mathematicians worry about coloring nodes of networks? Seems a rather strange thing to do, coloring things in, a bit childish. Well, actually, it's exactly the same problem as timetabling, and timetabling comes up in many contexts. And in fact, I would say more. You can transform this kind of problem much, much more than I've done. But maybe that will be discussed later on. So I think I've said enough on the economic case for supporting pure mathematical research in more or less its current form. And I would now like to turn to the cultural case. I, as I have said, am one of those individual mathematicians who do not directly strive to swell the national coffers. So let me spend some time explaining what it is about mathematical research that so appeals to me. Since mathematics is a very broad subject, and tastes and mathematical styles differ widely from one branch of this subject to another, this part of the lecture will inevitably be less universal and more personal than the first. However, I believe my experience is fairly typical. I hope that in France, of all places, a cultural argument will be taken seriously. My home country, England, was famously described by Napoleon as une nation de boutiquiers, a nation of shopkeepers. In England, the word intellectual is sometimes regarded as virtually a synonym for pretentious, whereas in France, intellectuals are widely admired and abstract thought greatly appreciated, or at least so one reads. The cultural case, in brief, is that knowledge is worth pursuing for its own sake. Just as one of the rewards for individual mathematical or other cultural success is a form of immortality, so entire societies, ancient Greece being the most obvious example, are remembered for their contributions to knowledge long after their political and economic influence has faded. A society that deliberately turns its back on the pursuit of knowledge is, to put it bluntly, a boring society. On the other hand, it would be foolish to suggest that all knowledge, or even all mathematical knowledge, is of equal value. What I shall do now is talk a little about a theorem that I definitely do find worth knowing for its own sake. Perhaps one day it will be useful as well, but for now, I present it as an example of beauty in mathematics. The idea that a piece of mathematics could have an aesthetic appeal puzzles those who have never experienced it, or perhaps I should say never knowingly experienced it. The theorem I've chosen as my example is very well known in the right mathematical circles, but it is not one of the giant theorems of the 20th century and is completely unknown outside mathematics. This is a deliberate decision on my part because I want to make the point that mathematical beauty is not confined to 1 or 2 spectacular and famous theorems, but lurks everywhere, waiting to surprise and delight us. So here comes another lot of numbers. Is there room for it? Not quite. Well, those are the numbers from 2 to 100. It's not immediately apparent that that's what it is, but if you do the sums that I've indicated, you will find that it really is the numbers from 2 to 100 in that order. So we go 2, 3, and then 2 by 2 is 4, 5, 2 times 3 is 6, and so on. So what I've done is write the numbers from 2 to 100 in their prime factorizations. I take each one and write it as a product of primes. And next to it in green, I've just written how many primes I needed. Let me just read out the beginning of that sequence. It goes 1, 1, 2, 1, 2, 1, 3, 2, 2, 1, 3, 1, 2, 2, 4, 1, 3, 1, 3, 2, 2. So is there any pattern that one can spot there? I don't know. It's not really... if you could really spot a sort of simple pattern, then probably you'd have made a mistake, but if not, you'd become very famous. It seems somehow rather sporadic and difficult to make head or tail of it. Well, in order to make head or tail of it, what I decided to do was just to count up how many of these numbers needed one factor, how many needed two factors, how many needed three, and so on. So a number that just needs one factor is precisely a prime number, whereas a number that needs 6, which happens twice with 64 and 96, is a product of lots of small prime numbers. And so here's a little table. 25 prime numbers, 34 numbers had 2 factors, and so on. And underneath I've just drawn a bar chart which encapsulates the information in the table above. Now, even a non-mathematician, if he's feeling particularly speculative, may notice something about the shape of this bar chart. It goes up, and then it goes down. But when it goes down here, it sort of slightly levels off at the bottom. This is a fairly familiar sort of shape. It's the well-known bell curve that comes up in probability. So it's sort of tempting, maybe a bit silly, but tempting, just to try to fit a bell curve to this thing. So that's what I've done here. Now you could object to that, saying that the bit on the left is not very realistic. But 100 is a small number as mathematical numbers go. And if you were feeling really sort of well, if you're just in dreamland, you might think, perhaps if you took a much bigger number, it would get a bit closer to a bell curve, and a much bigger number still. Well, this thought occurred to somebody called Katz, and he was a probabilist, so somehow the idea of a bell curve seemed reasonably natural to him. But it wouldn't have seemed natural to a number theorist in his day, because somehow the prime numbers are completely deterministic. Why should probability have anything to do with them? And he couldn't prove that the bell curve had anything to do with it, but he went and gave a talk in the Institute for Advanced Study in Princeton, and by good fortune, Paul Erdős was in the audience. He didn't seem to be concentrating all that much, but that never meant anything with Erdős, because by the end of the talk, he said he could prove that the bell curve did indeed genuinely occur. I'm not going to say much about this slide, but let me just say that it was known that the average number of prime factors of a number near a number n is the logarithm of n. And if you want to work out what that is and you're not very familiar with logs, roughly speaking, you take the number of digits of your number, multiply by 2.3, take the number of digits of that, and multiply by 2.3. That means if you start with a very big number, you get quite a lot smaller number at the end of that process. Well, a very nice theorem of Hardy and Ramanujan, which was greatly simplified by Paul Turan, was that actually not only is that the average, but most numbers are close to the average. Most numbers have roughly log n prime factors, but the summit of this sort of theorem was the Erdős-Katz theorem that resulted from this talk, that it really is true. This word normally distributed, this phrase, is the mathematical way of saying you do get a bell curve. Now, why is that a beautiful theorem? That's what it was supposed to be. Well, one reason is that there's something intrinsically satisfying about the normal distribution. Actually, it crops up absolutely everywhere in mathematics. It comes up in quantum mechanics. You name it, the normal distribution is everywhere. And so mathematicians who are used to it think of it as a very simple object. Another reason is that it reveals some sort of hidden structure in the primes. If I draw that picture, you don't really see a bell curve. You see a very vague suggestion of one, but you don't actually see it. And if you really wanted to see it, you'd have to produce an enormous number of factorizations, which is really beyond what one could reasonably do. So it's sort of hidden in the sense that you can't directly appreciate it. The third thing is I think that it's just a completely outrageous conjecture to make in the first place, that probability should have anything to do with the primes. And the fourth one, perhaps the most important of all, is that the proof is very beautiful, and I would just like very briefly to sketch that. So this is what was going on in Erdős's mind during the latter part of Katz's talk. Most numbers, as was known, have about log n prime factors, I'm going to do it in very brief qualitative terms. Therefore, most prime factors of most numbers near n are small, because if they're too large, then they would multiply to something bigger than n. Then you look at whether the number is even, whether it's divisible by 3, whether it's divisible by 5. A tool called the Brun sieve tells us that those events are sort of roughly independent. Now, Erdős, unlike Katz, lived and breathed the Brun sieve. That was really his big advantage. Had they been precisely independent, then you would expect a normal distribution, because that's where normal distributions come in. And 5, the most important of all, if you then add the numbers, you don't say small, large, and that kind of thing, you can actually get that sketch of an argument to work. That's something I'd like to stress, because there are many romantic stories about mathematicians who are going for a walk in the mountains, and they suddenly have an idea, and they know that they just have to go back home and write it all out, and they've got a wonderful theorem. There are some very famous examples of that. A more common experience for me is I suddenly have this wonderful idea, and I say to my wife, Emily, I think I've got it now. Can I just go upstairs for a while? And so I go upstairs. A little bit later, I come downstairs. A little bit later still, she finally gets around to asking, how did it go? I say, oh, so yes, no, it didn't really work. And I think that's probably, for every romantic experience where it does work, there are probably 99 that don't. And that's for the benefit of non-mathematicians. And mathematicians will, of course, know that what I'm saying is true, unless they're very different from me. Now I'm doing something rather ambitious. Not exactly attempting to define beauty, but at least to say a little bit about what beauty sometimes involves. So symmetry is obviously often a component of beauty, and balance, sort of nice compositions. Some sort of tension between simplicity and complexity. If something is too simple, it's not beautiful, because you can just see at a glance what it is. If it's too complicated, it's just completely haphazard and you can't really appreciate it. But something in between is where beauty seems to appear. Similar tension between regularity, irregularity, predictability, and unpredictability, and patterns that you can sort of appreciate but not immediately understand. And I think the Erdős-Katz theorem has many of those qualities. I've got a few pictures here. I'm hoping that you will agree with me that this arrangement of squares here is more beautiful than this one. Of course, neither is spectacularly beautiful, but this one is somehow a bit more satisfying than this one. Now, there is a perfectly sound mathematical reason for this. I've got a 13 by 13 grid, and here I take every 8th square going along like this, and here I take every 9th square. Now, 8 and 13 are consecutive Fibonacci numbers, so the ratio 8 to 13, or 13 to 8, is close to the golden ratio, and for very good mathematical reasons, that tends to lead to a nice balanced arrangement, whereas here I've got, I'm taking every 9th square, and 3 9s are 27, which is close to 2 13s, 26, and that leads to these rather unsatisfying sort of vertical-seeming stripes. Here I took the graph mod 13, this is just for the benefit of mathematicians, of x squared against x. That's a 0 along the bottom. And here I took a completely random arrangement. I chose each square with probability 1 over 8. It's quite interesting to compare them. The random one is actually not completely unsatisfying, I think. It's got a certain balance to it. This one's got a bit of symmetry. You can actually make these comparisons. So I think it's not completely outrageous to talk about beauty in mathematics. So I hope that even if the Erdős-Katz theorem has not just given you an intense aesthetic experience, you can at least see how it might do so for those who spend their lives devoted to mathematics. I would like to end by returning to the word importance, because, interestingly enough, the beauty of some mathematics contributes to its importance. This is not just because we want as much beauty in the world as possible. After all, the beauty of higher mathematics is appreciated by only a tiny minority of the world's population. The more serious reason is that there is a remarkable correlation between mathematics that is beautiful and mathematics that is important. This is partly for reasons internal to mathematics. There are two ways in which the subject develops. One is the solution of problems, which involves clever, unexpected ideas and hard technical work in varying proportions. Now, if mathematics were nothing but problem solving, then as it grew and grew, it would become more and more chaotic, specialized, and difficult. And indeed, to some extent, this does in fact happen. Fortunately, there is a tendency in the opposite direction as well. It often happens that there are similarities between the solutions to problems, or between the structures that are thrown up as part of the solutions. Sometimes these similarities point to more general phenomena that simultaneously explain several different pieces of mathematics. These more general phenomena can be very difficult to discover, but when they are discovered, they have a very important simplifying and organizing role and can lead to the solutions of further problems or raise new and fascinating questions. I've just argued that a serious component of aesthetic appreciation is the feeling that a complicated pattern has been generated in a simple way, but not so that one can immediately apprehend it. It should not come as a total surprise, therefore, that when a number of loosely related specific results turn out to be consequences of the same general one, mathematicians should have an aesthetic response. In fact, an appreciation of beauty is essential, or at least very useful indeed, for solving problems as well. Often one can reject a line of attack on the grounds that it is simply not elegant enough to work. One may be wrong, but it is still efficient to look for beautiful solutions first and settle for ugly ones only as a last resort. Similarly, finding the solution of a problem involves a great deal of rather vague reasoning, following hunches, making guesses, and so on. How does one know whether one of these guesses will survive a later, more rigorous scrutiny? Well, one doesn't, as I stressed earlier, but it is a good rule of thumb that the more beautiful the guess, the more likely it is to survive. I want to illustrate this with I apologize, it's a rather frivolous transparency. It's an illustration from a children's book, and I'm putting it up as an example of something that is not beautiful. This is a picture of an elephant that has been surprised and is squirting some water out of its trunk. Now, any mathematician, and I think any non-mathematician, will look at it and find something rather unsatisfactory about that picture. Now, I'd say that the primary response is just an aesthetic one. It just doesn't look right. It's not nice. One can then go further and analyze it and say that this ought to be more like a parabola, but it isn't. Or a simpler proof that it just isn't right is that it initially squirts more or less directly vertically, but doesn't come back and land on the tip of the elephant's trunk again. What is making the water move over in this direction? It's a complete mystery to me. Even if there were a strong wind, it wouldn't look right, I think. So aesthetics can sort of guide you, I think, to some kind of mathematics as well. But there are also external reasons. I suppose this is an external reason for the importance of beauty. The mathematician Eugene Wigner once gave a famous lecture entitled The Unreasonable Effectiveness of Mathematics. In fact, it's so famous that it's something of a cliché in mathematical circles even to mention it. He was referring to the fact that the physical world obeys very simple mathematical laws, such as Newton's inverse square law of gravitation, and it is hard to explain why this should be. Could one not conceive of a world in which science was impossible because there simply wasn't enough regularity? Mathematics would still be possible in such a world, though whether it would be pursued is another matter, because simple and elegant mathematical models would have no physical counterparts. I don't think this philosophical question has been satisfactorily answered, but we can be grateful that in our world it is possible to use simple mathematical models. These can describe or even explain the great complexities of physics and to a lesser extent the other sciences. Once again, complexity arises from simplicity, and once again, beauty reveals itself to be important. Thanks to this piece of good fortune, we can be confident that mathematicians, if they are given the freedom to pursue the subject that gives them so much pleasure, will continue to produce a body of work that is important in every sense of the word.